Welcome to the deep dive. We're about to go deep on circular motion.
It's everywhere you look, really. From planets and stars all the way down to spinning wheels. It's fascinating.
Okay, so to really get this, we got to start with vectors, right? I always mix those up with scalar quantities. Can you help me out with why those are so important here?
Sure, vectors matter because they show us both the size and the direction of something, like velocity.
Right, velocity.
If you just say a car is going 60 miles per hour, you're missing half the story. Got to know where it's going to. Vectors give us that full picture.
Like an arrow pointing the way. Makes sense.
Exactly. And then there's the cross product, something we do with vectors, especially important for circular motion. And it helps us understand things like torque and angular momentum.
Oh yeah, the cross product. I've heard of the right-hand rule for that. Honestly, it's always felt like a magic trick to me, not really math.
Huh. It does involve thinking about things in 3D, but it's not magic. It's just a neat way to figure out which way the new vector points after a cross product.
So the new vector, it's always at a right angle to the first two.
Right, you got it. And remember, the order matters with cross products. A cross B isn't the same as B cross A. Unlike multiplying regular numbers, switching them up changes the result.
Gotcha. Okay, so vectors, check. Now let's talk circles. What exactly is circular motion?
Well, it's when something moves along a circular path, always stays the same distance from a fixed point.
Like the Earth going around the sun.
Perfect example. We're constantly moving, but always about the same distance away.
Simple, but there's got to be more to it than that.
Yeah.
What else do we need to know?
Well, we've got the center. That's the fixed point everything revolves around. Then there's the radius, the distance between the object and the center. And the radius vector, that's a vector pointing from the center to where the object is.
So the radius vector is always moving, like an arrow pointing from the sun to the Earth as it goes around.
Exactly. Now, how do we measure how far something travels along that circular path? That's where angular displacement comes in.
Angular displacement. So we're talking angles here.
Yep. It's the angle the radius vector sweeps out as the object moves. Think of a clock. The minute hand goes from 12 to 3. That's 90 degrees of angular displacement.
Oh, I see. What units do we use for that?
We can use degrees, radians, or revolutions. Degrees you probably know. But radians are common in physics. A full circle is 360 degrees or 2 pi radians.
So we've got angular displacement, but what about the speed along that circular path?
That's angular velocity, written with the Greek letter omega. It's how fast the angular displacement is changing.
So not just how much it moves, but how quickly it's going through those angles.
Right. And it connects directly to linear velocity, the speed we usually think about. There's a simple formula. V equals R omega.
So if something's farther from the center of rotation, it'll have a higher linear velocity, even if the angular velocity is the same.
Exactly. Think of a merry-go-round. The horses on the outer edge are moving faster than those closer to the center, even though they all finish a revolution in the same time.
That makes sense. What happens when the merry-go-round speeds up or slows down?
Well, then we've got angular acceleration, written with the Greek letter alpha. It's the rate of change of angular velocity.
So if the merry-go-round spins faster, it has angular acceleration. But if it spins at a steady speed, even though it's moving, the angular acceleration is 0.
Exactly. No change in angular velocity means no angular acceleration.
Okay, so angular displacement, velocity, and acceleration. Got it. What about the forces involved, though? What makes something move in a circle in the first place?
That brings us to centripetal force. It's key to circular motion.
Centripetal force. Okay, tell me more.
It's any force that pulls towards the center of the circle, keeping the object from going straight. Not a new kind of force, just any force acting that way.
So it could be gravity, like with the satellite, or the tension in a string if you're swinging something around.
Exactly. And the strength of that force depends on the object's mass, speed, and the circle's radius.
So a heavier object moving faster in a tighter circle needs a stronger force to stay on track. Starting to get the picture.
Great. Now let's think about something you do all the time, driving. What about turning a corner in a car?
Oh yeah, good point. I've always wondered about the physics of that.
Well, the friction between your tires and the road. That's providing the centripetal force to keep you from skidding out.
What about those banked curves on highways, though? Do those have anything to do with this?
Oh, absolutely. By tilting the road, engineers use a part of the normal force, that's the force from the road, pushing up on the car.
I see, so it helps push the car inwards.
Exactly, and that's really important at higher speeds. On a flat curve, friction alone might not be enough.
So the banked curve helps cars go faster around the bend safely. That's cool. It's like physics working in everyday life without us even realizing it.
It is. And speaking of cool examples, there are some things where circular motion seems to defy gravity, like the conical pendulum or those rotor rides at carnivals.
I was just thinking about those. They always seemed like magic to me. But now I bet we can understand what's going on.
They do seem counterintuitive, but they're great examples of how circular motion is all about balancing forces.
I'm ready to dive into those,
Mhm.
but I feel like we've already covered so much.
We have. Let's take a moment to let all this sink in, then we'll tackle those examples.
Okay, let's get into those mind-bending examples you mentioned. The conical pendulum and the rotor, or death well. I always thought those were just magic, but I'm ready to see the physics behind them.
They do seem kind of impossible at first, but they show us just how important balancing forces is in circular motion.
Right.
So the conical pendulum first.
Okay, what exactly is a conical pendulum?
Imagine a weight on a string, but instead of swinging back and forth, it swings in a horizontal circle. The string makes a cone shape as it moves. That's where the name comes from.
I can picture it. But what keeps that weight going in a circle? Isn't gravity pulling it down?
It is, but the tension in the string is doing two things at once. It holds the weight up against gravity, and it's the inward force, the centripetal force, that keeps it moving in that circle.
Oh, so the tension's like split into two parts. One fighting gravity, the other keeping it moving in a circle.
Exactly. The horizontal part of the tension is our centripetal force.
That's pretty neat. Okay, now what about the death well? I've always wondered how people stick to the wall without falling out.
It's all about friction and that normal force. When the cylinder spins, you feel pressed against the wall, right? That's the normal force pushing in.
Yeah.
If it spins fast enough, the friction between you and the wall gets strong enough to balance out your weight so you don't slide down.
Wait, friction is holding me up. I thought friction always worked against the direction of motion.
Well, it does, but the motion it's working against here is you sliding down. It's keeping you in place by working against gravity.
So the faster the spin, the stronger the normal force, the more friction, and the better I stick. Even without a harness. That's crazy.
It is. It shows how simple things like friction and the normal force can do amazing things when you add in circular motion.
All right, and speaking of amazing things, we got to talk about centrifugal force. I know it's not a real force, but it definitely feels real on a spinning ride.
Right. It's a tricky one.
Yeah.
Centrifugal force is what we feel as an outward push when we're spinning. But from someone standing still, watching, it's not a real force acting on us. It's our inertia, that tendency to keep moving in a straight line.
So it's like, from my perspective on the ride, it feels like a force pushing me out. But from someone on the ground, they just see me trying to get going straight while the ride's pulling me in a circle.
Exactly. They see the centripetal force pulling you inward. You feel centrifugal force because your body is resisting that pull.
Kind of like when you get pushed back in your seat when a car accelerates.
That's a perfect analogy. It all comes down to your perspective, your frame of reference.
Okay, so we tackled those examples, but I feel like we've only scratched the surface of circular motion. What's next?
Well, we've talked about forces, but there's another big concept tied to this. Energy.
Energy. How does that fit in?
Just like with anything that moves, objects in circular motion have kinetic energy.
Right, because they're moving.
And if they're in a force field, like gravity, they might have potential energy too, depending on where they are.
So a satellite going around the Earth has kinetic energy from its motion and potential energy because of Earth's gravity.
You got it. And just like in other systems, the total energy, kinetic plus potential, stays the same in circular motion.
So as the satellite orbits, if energies are constantly changing, but the total amount stays constant, that's conservation of energy, right?
You nailed it. And this is really important for understanding how things behave in circular motion, especially when speed or distances change.
Wow, it's like this cosmic puzzle. Forces, motion, energy, all connected.
It is a beautiful puzzle. The more you look at it, the more you see how elegant it is and how far-reaching the implications are.
You know, this is making me realize that circular motion isn't just about rides and satellites. It's like fundamental to some of the biggest things in the universe.
Yeah, absolutely. From how galaxies form to the orbits of planets, circular motion is built into the cosmos. It's the same physics here on Earth as it is out there with the stars.
Okay, I am officially hooked. Now I want to explore those cosmic connections. How does circular motion shape the universe? But I think we need a little break first to let all this sink in. Okay, I'm ready to keep going. My mind's still blown from what we talked about with circular motion. It's like a whole new way of looking at things.
It really is fundamental. So much in the universe relies on it. And like we said, now we're going to see how it all connects to the cosmos.
Perfect. I'm ready for that mind-blowing journey through space you promised. Let's start with galaxies. I've always loved those spiral shapes, those swirls of stars and gas. How does circular motion help create those?
It's all about the spin. Imagine a huge cloud of gas and dust. That's where galaxies come from.
Okay.
As the cloud collapses under its own gravity, it starts to rotate.
So it's like a figure skater pulling in their arms. They spin faster as they get smaller, right?
Exactly. As the cloud shrinks, it spins faster and eventually flattens into a disk shape. Stars start forming in that disk, and they keep that spinning motion.
And those stars keep orbiting the center of the galaxy,
Yeah.
making those beautiful spiral patterns. That's amazing. The same stuff we've been talking about is shaping those huge structures.
It all comes back to the same physics, and closer to home, our own solar system formed the same way.
So all the planets, including Earth, are doing this cosmic dance around the sun, held in place by gravity.
Yep. And those orbits, those elliptical paths, that's because of the planet's initial speed and the sun's gravity pulling on them.
Wow, it's mind-blowing. The same physics for a spinning top, it also governs the planets and the stars.
Yeah,
We're all part of this giant cosmic ballet.
they are. Circular motion, it's everywhere in the universe, from the tiniest particles to the largest things out there.
This deep dive has really changed how I see the universe. It's amazing how something as simple as an object moving in a circle can be so important.
It is, and it's been great exploring it all with you. But we always like to leave our listeners with something to think about.
Yeah, give us a question to ponder as we keep looking at the world around us.
All right, so here it is. Next time you see something moving in a circle, whether it's a spinning wheel, a dancer twirling, or a planet in the night sky, take a second to think about all the forces involved.
And the energy keeping it all going.
Exactly. That same dance is happening all over the universe, shaping everything around us.
Thank you for joining us on this deep dive into circular motion. We hope you learned something new and maybe even see the world a bit differently now. Keep exploring, keep asking questions, and keep diving deep.